Good day all. The Sources project is part of the Environmental Geoscience program, and it is a fully externally funded project that has three components. I'm really only going to talk to you about the geochemical map of an oil sands plume initial results. The other two activities are legacy publications and legacy data from the previous round of EGP, which is producing quite a few papers, and good science for environmental sustainability of the oil sands. And Jason Ahad has an externally funded activity that is scheduled to commence in this fiscal year, 2021. This activity is to build a reactive transport model around a small tailings-water plume discovered in the previous EGP cycle. Here are the main project members. There are, of course, others, but this is the five main components and investigators. Where were we from the last EGP? That shaded area on the map is really where we intersected the oil sands plume, and you can see it with those boron contours in white there, the 100, 200, 300 contours. We didn't really have great definition. There was clearly something coming in at that seep indicated there. The tailings pond is off on the top left, and it moves into that wetland fen on the bottom center right, with dry jack pine forest to the north and south. So this little wetland is receiving this small amount of leakage from the tailings pond, and seeing this is the first one anybody's ever found, it's obviously quite important to understand what is going on and what are the reactions, what are the takeaway messages and science that we can derive from this site. The things 80% less than 10%, less than 10%, that's the naphthenic acid data to date. From at the seep, of course, you've got very high tailings pond input. This is Jason Ahad's work, but the nearest samples we have to that, it's already decreased to zero effectively by the amount that you can tell from the method. So the objective, of course, is a detailed plume coverage to really see if we can understand what's going on. So that's what we did. We did a detailed 10 by 10 meter grid of ground and surface water. And as you can see, here's the surface water boron contours, and we have great definition now of a 400, 300, 200, 100 ppb. And what you see is a very rapid attenuation of the signal within 60 meters. That is in comparison to the greater than 500 meters of flow path that it's actually taking to get here. So whatever's happening in the wetland is really very efficient at attenuating some of the components of the oil sands tailings plume. And that really is what we want to understand, is how is that happening, and can it really help us with some of the sustainability issues of these tailing ponds. If you look at the groundwater, that was the surface water. This is the groundwater, much more difficult pattern to represent. In this grey shading there, sort of the best plan representation you can make of subsurface aquitard barriers to flow. And what you can see is that the tailings pond plume follows a specific pathway out of that area and into the wetland. Whereas best we can tell, it's all at background. So we're at dilution there, or we've actually fully attenuated the plume. Either way, there is no evidence that the plume reaches the Muskeg River down in the bottom there, which is a good thing. If we go from boron to potassium, which is a more conservative element, in other words, it tends to stay in the solution more than boron. Boron does sorb. Then what you see is sort of similar to the boron surface water contours, but a little bit less. So it's much more likely that this is representing true dilution than the boron, which is a bit more reactive. So from that we can actually play boron and potassium off and come up with an attenuation contour map for boron. So this is basically the contours which have been extracted with minus dilution. Dilution has been accounted for. And what you see is that in the center of the plume, around the 80% seep mark, is actually now possibly even a boron source that it's actually desorbing under these conditions, and then it moves out to the out to the northeast there, and what you see there is 40, 80, 120 contours that show a very rapid decline in the boron contour, boron concentration. This is all the hallmarks of a reactive transport sorption reaction front. So this is a very good clue as to some of the things that are impacting boron in this locality. And unfortunately, as I said, I'll put again the 80% and the less than 10% contours of naphthenic acid concentrations on here. And so what you're seeing is we don't quite have the detail coverage that we would like. It's also interesting that on there is the actual preferred flow path of the groundwater, and you're not really seeing it represented in the surface water pattern. So suggesting that there really is a bit of decoupling going on here. One of the things that is really interesting to look at for something like this is that what we want to see is how does this impact is this the same pattern that you see with naphthenic acids? Is it, we're also doing eDNA, is there any microbial changes along this pathway? And a lot with these rapid changes and especially at that reaction front. So it's early days, but the plume is now well defined. Rapid plume attenuation is clearly through reactive transport plus dilution, but we can extract the dilution factor, and it shows that we have really a very good data set within which to frame what's going on. The plume does not seem to reach the river, and there's much more sample analysis still to go. Those are the papers that we've generated this year, and we've got a bunch more that are being in this COVID written and just about to be submitted or have been submitted during this COVID shutdown. Thank you, and any questions, there are my contact details.